Welcome back to the deep dive. We have a highly specific mission today, and I'm talking directly to you, the listener, right now.
Yeah, we've got a really interesting one today.
We do. Our goal is to take a pretty dense, cutting-edge AI research paper and unpack it into a conversation that actually clarifies the mechanics of where this technology is heading.
Right, because the progress in this field has reached a point where, understanding the trajectory requires us to look under the hood.
Exactly.
We have to look at the actual engine driving the computation.
Hmm.
We're moving way beyond theoretical algorithms now and dealing with the physical realities of silicon.
So for our source material today, we're pulling from the foundations of the generative artificial intelligence frontier. And specifically, we are analyzing a really foundational paper published in July 2024.
A huge paper.
Oh, massive. It's titled FlashAttention-3. Fast and accurate attention with asynchrony and low precision. And the pedigree of the authors on this one is, it's pretty notable.
It's an absolute super team.
Right. We're looking at a collaboration between researchers from Colfax Research, Meta, NVIDIA, Georgia Tech, Princeton, and Together AI. They basically pooled their resources to solve a massive structural bottleneck in computation.
A bottleneck that ultimately dictates the boundaries of what these AI systems can process in any reasonable time frame.
Now, you might be wondering why you should care about the intricacies of GPU utilization. I mean, it sounds dry, right?
It does sound a bit like a spec sheet.
But this paper details the exact architecture that actively unlocks the ability for large language models to process massive inputs.
Yeah, we're talking about reading entire textbooks in a single prompt.
Exactly. Or analyzing sprawling code bases, or evaluating long-horizon video data without the system just completely freezing or running out of memory.
It bridges the gap between those theoretical context windows we hear about and actual functional performance.
Right. Okay, let's unpack this. What is the core structural issue we're actually examining here?
Well, to understand the issue, we have to look closely at the attention mechanism within the transformer architecture.
The famous attention is all you need.
Exactly. Attention is how the model assigns weight to different tokens in a sequence to figure out the context. But the fundamental characteristic of this mechanism is that it scales quadratically.
Meaning that as the context window expands, the computational tax doesn't just scale linearly, it compounds.
Precisely. If you double the length of the input sequence, the amount of computation required actually quadruples.
Ouch.
Yeah. So as we push models to handle larger and larger context windows, this quadratic scaling creates just an enormous bottleneck. It necessitates reading and writing massive amounts of data to the memory chips on the hardware.
Which brings us to the baseline for today's discussion, which is FlashAttention-2. It was a really highly regarded piece of software that optimized those memory reads and writes.
It was the industry standard.
But the researchers point out a rather shocking statistic in the text. Even with all of its optimizations, FlashAttention-2 was only achieving about 35% utilization on NVIDIA's Hopper H100 GPUs.
Yeah, 35%. Which raises a really important question. Why was state-of-the-art software leaving nearly 2/3 of the compute capacity on a premium accelerator chip completely idle?
So it's not a limitation of the raw hardware capability, it's a fundamental mismatch in how the software is instructing the hardware to operate.
That is the absolute crux of the issue. FlashAttention-2 operated on a synchronous execution model.
Meaning it dispatched tasks sequentially.
Right. However, the Hopper architecture is designed with highly specialized, physically distinct hardware units. You have your tensor cores, which are dedicated purely to matrix multiplication.
The heavy math.
And then you have the tensor memory accelerator, or the TMA, which is designed specifically to handle data movement.
Okay.
The synchronous model of FlashAttention-2 forced these distinct units to wait on each other.
Let's ground this with a structural analogy for a second. Imagine a high-end commercial kitchen where the kitchen itself represents the accelerator chip.
Okay, I like this.
So in a synchronous model, you have a master chef who walks over to the walk-in refrigerator, gathers a single ingredient, carries it back to the stove, cooks it, and only then realizes the next step requires another ingredient.
Right, so the cooking halts entirely while the chef walks all the way back to the refrigerator.
Exactly. It's wildly inefficient.
It is. Let's take that kitchen idea a step further to really capture the hardware dynamic.
Go for it.
The master chef is your tensor core. The matrix multiplication is incredibly fast, but the walking back and forth to fetch ingredients from the walk-in refrigerator, which represents the global memory on the chip, takes an eternity by comparison.
So in asynchronous execution, the stove just sits cold while the chef is in transit.
Exactly, which introduces the first major architectural shift in FlashAttention-3. The researchers implemented what they call producer-consumer asynchrony.
Producer-consumer. Okay, how does that split the workload?
Well, FlashAttention-3 takes advantage of those distinct hardware components. They utilize a technique known as warp specialization.
And a warp is basically just...
A warp is simply a collection of threads that execute simultaneously. So the developers assign specific warps exclusively to act as producers and other warps exclusively as consumers.
Evolving our kitchen analogy here, this is where we actually divide the labor.
Yes.
The producers are your dedicated prep cooks utilizing the tensor memory accelerator. Their sole responsibility is to constantly fetch ingredients from that massive, distant walk-in refrigerator.
Which is the HBM, or high bandwidth memory.
Right, the HBM. And they take those ingredients and put them onto the counter right next to the stove, which acts as the incredibly fast shared memory.
While the master chefs, the consumers running the tensor cores, never step away from the stove. They simply pull from the prep counter and execute the math.
They just cook nonstop.
Nonstop. And to fully appreciate why this division of labor is so necessary, you have to look at the physical memory hierarchy of the H100 chip details in the paper.
The numbers are pretty wild.
They are. At the top level, you have the global memory, the HBM. It offers a massive 80 gigabytes of capacity, but the latency to access it is significant. It's far away.
Right.
But as you move physically closer to the processing cores, the memory access speeds up dramatically, but the capacity shrinks just as drastically.
Yeah, it drops off a cliff.
Down at the register memory level, right on the streaming multiprocessor itself, you are limited to just 256 kilobytes.
From 80 gigabytes down to 256 kilobytes. That is an extreme constraint on local storage.
It forces a highly specific operational flow. It's the equivalent of having a sprawling warehouse of ingredients a mile down the road, but a cutting board that can only hold a handful of diced vegetables at a time.
That's a great way to put it.
What's fascinating here is how the FlashAttention-3 software is custom-tailored to map perfectly onto this physical terrain.
Because the prep cooks are continuously cycling data from the warehouse to ensure that tiny cutting board is never empty.
Exactly, allowing the master chefs to operate at maximum continuous throughput.
But getting the data to the cores efficiently is, it's really only half the battle, because the paper outlines a secondary bottleneck that occurs right at the stove.
Yes, the math itself.
Right. Even with the ingredients constantly available on the counter, the processors were still stalling. And this is due to a stark disparity in processing capabilities for different types of mathematical operations on the chip.
Yeah, the hardware is not uniformly powerful across all functions.
I saw this number in the paper and I had to read it twice. On the H100, the processing power for matrix multiplication is 989 teraflop PS.
Which handles the core linear algebra very fast.
Right. But for special functions, like the exponentials required for the Softmax calculation within the attention mechanism, the hardware only provides 3.9 teraflop PS of processing power.
The Softmax computation is roughly 256 times slower than the matrix multiplication.
Wait, so if the Softmax is that slow, that means the incredibly powerful matrix multipliers are basically just sitting idle the vast majority of the time, just waiting for that specific operation to finish.
And that is exactly what happens due to the sequential dependency of the standard attention algorithm.
And because you have to do them in order.
Right. You perform a massive high-speed matrix multiplication, a GMM operation, but then you are required to take the results of that GMM and process them through the exceptionally slow Softmax calculation.
So you literally cannot begin the next rapid matrix multiplication until the Softmax is complete.
It forces a high-performance system to continuously hit the brakes to accommodate a slower component.
So when you're dealing with a physical hardware limitation where the silicon simply processes exponentials slower, the solution isn't to change the math itself, right?
No, you can't cheese the math.
So the researchers introduced an organizational trick they call ping-pong scheduling.
Ping-pong scheduling. It's an elegant software pipelining technique. Since they cannot accelerate the physical Softmax hardware, they chose to hide its latency.
Hide it? How?
They take the consumer warps our master chefs and divide them into two distinct groups, Warp Group 1 and Warp Group 2.
Operating like two independent stations on the exact same stove.
Precisely. While Warp Group 1 is executing the rapid GMM matrix math, Warp Group 2 is simultaneously processing the slow Softmax calculation from the preceding step.
Because they use different units.
Exactly.
Okay.
Because these operations utilize different specialized units on the chip, they can execute concurrently.
Ah.
The moment warp group 1 completes its fast math and hits the Softmax requirement, the groups literally swap roles. Warp group 1 begins its slow Softmax, and warp group 2 immediately launches into the next fast GMM operation.
They are continuously passing the execution state back and forth. Ping pong.
Ping pong.
For you listening, this really highlights a critical aspect of systems engineering. They didn't invent some new algorithm. They mapped the instructions so perfectly that the latency of the slower hardware unit is completely masked by the execution of the faster unit.
They literally hid the slow math underneath the fast math to keep the pipeline completely saturated.
That is just brilliant.
The utilization improvements from this ping pong scheduling are substantial.
Yeah.
But the research doesn't stop at scheduling.
No, it doesn't.
The third major optimization ventures into a very delicate area of numerical representation. They are really attempting to push the hardware to its absolute limit here.
Here's where it gets really interesting. We need to examine the low precision gamble.
Yeah, the precision shift. There is a broader industry trend toward utilizing lower precision data formats to accelerate computation and reduce memory bandwidth requirements.
Shrinking the numbers.
Right. Historically, models operated heavily on FP16 16-bit floating point precision. But recently, the objective has been to transition to FP8.
Which halves the memory footprint and effectively doubles the theoretical throughput, right?
Exactly. There are even architectures out there pushing toward FP4 now.
But reducing the bit width of your numerical representation introduces some really significant dangers.
It does.
The FP8 format only allocates 3 bits for the mantissa, which are the significant digits, and 4 bits for the exponent, which determines the scale.
That is a highly restricted dynamic range to capture complex neural network activations.
It's a tiny box to fit data into.
And the primary risk involves the presence of outliers. In large transformer models, it is well documented that certain activation features will sporadically spike to values orders of magnitude larger than the rest of the distribution.
So if you attempt to define your scaling factor based on one of those massive outliers,
The entire distribution gets compressed.
right, all the typical smaller values just get crushed to 0 within that limited 3-bit mantissa space, and you completely wash out the granular detail of the model's activations.
Exactly. This precision loss manifests as catastrophic mathematical error during the forward pass, which degrades the model's output quality severely.
So how do you fix it without losing the speed?
To mitigate this while maintaining the speed of FP8, the researchers deployed 2 specific techniques. The first is block quantization.
Basically breaking the tensors down rather than evaluating them globally.
Yes. The standard approach was to determine a scaling factor for an entire tensor matrix based on its absolute maximum value.
Which makes it vulnerable to that one huge spike.
Right. So block quantization divides the tensor into localized blocks and calculates an independent scaling factor for each block individually. They execute this step immediately after the rotary embedding operation.
So this confines the disruptive impact of an outlier strictly to its local block.
Exactly, preserving the precision of the surrounding data.
But the second technique is what really addresses the outlier issue at its core, I think. It's referred to as incoherent processing. Can you translate the mechanics of this operation for us?
I can try. At a mathematical level, incoherent processing involves multiplying both the query and key matrices by a randomized orthogonal matrix, specifically a variant of a Hadamard matrix prior to quantization.
Okay, let's visualize how this acts on the data distribution so we don't get lost in the math.
Good idea.
Imagine a canvas covered in an even layer of light paint, representing our normal data. But right in the center, there is a thick, heavy clunk of dark paint, which represents our outlier.
Okay.
If we simply press a flat frame over this canvas, which is analogous to standard 8-bit quantization, that thick clump is going to spread unpredictably and ruin the surrounding area.
It'll smear everywhere.
Right. So applying the Hadamard matrix is functionally equivalent to taking a brush and mathematically smearing that thick clump of dark paint perfectly and evenly across the entire canvas before applying the frame.
That's a really good way to picture it. Because the energy of the outlier is distributed uniformly across all dimensions, the magnitude of the spike is reduced dramatically.
The spike is gone.
No single point in the matrix is large enough to force a destructive scaling factor anymore. The outlier is smoothly blended into the overall distribution.
And the critical feature of using an orthogonal matrix for this process is its reversibility, right?
That is the key. An orthogonal matrix is its own inverse, or closely related to it. Because the transformation is mathematically reversible, the underlying inner products of the attention mechanism remain completely unchanged.
The models calculate the exact same relationship.
Exactly. But by smoothing the spikes prior to the low-precision compression, the catastrophic quantization errors are bypassed entirely.
So the system successfully mitigates the precision loss while fully capitalizing on the speed of the 8-bit hardware units.
Yes.
And the resulting performance metrics from combining these techniques are just exceptional.
You really are. By integrating the asynchronous memory fetching, the ping-pong scheduling to mask latency, and the localized block quantization with incoherent processing.
All of it together.
Right. The FP8 implementation of FlashAttention-3 achieves a throughput of 1.2 petaflops per second on a single H100 chip.
We are crossing the quadrillion operations per second threshold on a single card. That is staggering.
It is. Furthermore, due to the effectiveness of the incoherent processing, this FP8 model doesn't just match baseline accuracy.
It beats it.
The data shows it is 2.6 times more accurate than a standard baseline FP8 attention implementation. It extracts the raw speed of the low-precision format while actively improving the numerical stability.
So what does this all mean when we evaluate the empirical validation in the paper? Because the researchers proved this on physical hardware, not just in simulation.
Real-world results.
Yeah. Compared to its predecessor, FlashAttention-3 operates up to 2.0x faster. When running in standard FP16 precision, it sustains 740 teraflops per second, which represents an impressive 75% utilization of the hardware.
They successfully bridged that massive idle gap we discussed at the start.
They really did. And when benchmarked against standard PyTorch implementations, it executes up to 16 times faster.
16 times.
It even outperforms highly optimized closed-source vendor libraries like NVIDIA's cuDNN, specifically in long sequence processing.
If we connect this to the bigger picture for a second,
Yeah.
the true value lies in its integration.
Us.
This architecture is open source. It becomes embedded into the foundational libraries that the entire industry relies on, such as PyTorch and the Hugging Face ecosystem.
So it's everywhere.
It acts as a passive infrastructure upgrade for every developer building generative models. You just update your library and suddenly everything is faster.
It effectively recalibrates the baseline of what is computationally feasible.
It does. By significantly widening the attention bottleneck, we expand the scope of permissible inputs. This exact architecture is what structurally enables multimodal AI to process uncompressed, high-resolution medical imagery.
Or to analyze hours of continuous audio data.
Exactly. And to support long-horizon agent workflows, where an AI system has to maintain context over thousands of complex sequential tasks.
It optimizes the underlying compute so thoroughly that deploying advanced, massive context models becomes economically and functionally viable for regular developers.
It makes the magic of AI cheaper and more accessible.
When we look at how FlashAttention-3 had to literally reorganize how a GPU physically breathes, separating the memory fetchers from the math crunchers, playing ping-pong with operations to hide hardware latency, and mathematically smearing data distributions just to squeeze into smaller formats.
It's an incredible feat of engineering.
It really is. And it makes you wonder, as we move into a future of even larger models, are we eventually going to hit the absolute physical limits of silicon? Or will human ingenuity keep finding ways to hide the math in the shadows? Think about that the next time you ask an AI to summarize a 500-page book in 3 seconds.